Let's see an example of this. And this example concerns estimating an expectation of some function of random variables. So an important case where you can apply the Monte Carlo integration methods is when we want to find the expectation of g of x for a random variable x with probability density f on some region A. So the support of x is the region A. Then in this case, the expectation we try to find, theta, is equal to EF of gx, which is given by the integral over the region A of g of x times the density fx dx. If the density fx is not directly sampleable, so we cannot directly sample from fx, or the density fx can be easily sampled from, however, we want a more efficient estimator for theta, then we can apply the importance sampling methods. Because theta is equal to this integral, which is equal to the integral over a of g of x times f of x divided by phi of x times phi of x dx, we're essentially dividing and multiplying phi at the same time, we may estimate theta by sampling from a distribution phi and computing theta hat, which is equal to the sample mean of gx divided by phi of x. So this part. In this case, our importance function is no longer f. Our phi is the importance function. That is the distribution we want to sample from. Given by the earlier rule of sums, we want to choose a distribution phi so that it satisfies phi of x is greater than 0 for all of the possible x's in the region A. In other words, the support of the random variable with density phi has to be larger than or equal to the support of the random variable x with density fx. Also, in order to reduce the variance of our theta hat, in other words, increasing its efficiency by reducing the MSE, phi is roughly proportional, ideally, to the absolute value of gx times fx, which is equal to the absolute value of gx times fx, because we know fx is non-negative. Let's see an example of how different choices of phi can affect the variance of the Monte Carlo estimator. Again, for this week's examples, you will be able to find the code inside examples week4.rmd. For some of the examples, the code is incomplete. You can search IC underscore to find all of the incomplete code chunks. And then you'll be able to find all of the complete code in the lecture slides and in the videos. Okay, so for our example, we want to evaluate the integral theta, which is equal to the integral from 0 to 1 of this thing. So e to the negative x divided by 1 plus x squared dx. You can see that theta is the expectation of g of x, which is equal to this thing over here, e to the negative x divided by 1 plus x squared, when x is the random variable following the standard uniform distribution. So in this case, the density fx is given by 1 for any x value between 0 and 1. Thus, we can think about theta as the integral from negative infinity to infinity of g of x times fx dx, which is equal to the expectation of the random variable g of x under the density f. In this case, fx is equal to 1 on the interval from 0 to 1, and is equal to 0 otherwise. This is the uniform density. So our problem is how we can estimate the theta using importance sampling. Let's stick with the earlier formulations and estimate theta by theta hat, which is equal to the sample mean of gx times fx divided by phi of x, where the x's are random draws from the importance function, importance distribution phi. So here we know that g of x times fx is equal to e to the negative x divided by 1 plus x squared, and then times the indicator function between that x is between 0 and 1. So this is essentially the uniform density. So we know that in the region of from 0 to 1, it's equal to 1, and outside the region, this should go to 0. We will consider 5 possible choices of the importance function phi. And the question we want to ask is which one works better. So you can see that for the 5 phis that are listed over here, so phi of 1 all the way to phi of 5, phi 1 all the way to phi 5, these are all valid probability densities that satisfy that phi of x is greater than 0 for x between 0 and 1. So that's our A, the region we want to integrate. So the question we want to ask is which one works better? Which one will give us a theta hat that is more efficient? Let's take a look at each of them. So here's the first one. Phi 1 of x is equal to 1 for any x between 0 and 1. So you can see that this is essentially the standard uniform density. So phi 1 is actually the same as our f over here. So choosing phi 1 as the importance function is essentially equivalent to implementing the simple Monte Carlo estimator. In other words, we sample from uniform 0, 1, which is our phi 1, and then we have the theta hat that is given by the fx times gx divided by 1. So we just take the mean of all of them. The pro for using this density as our importance function is that uniform 0, 1 is very easy to sample from. And at the same time, phi 1 is also bounded between 0 and 1. So it has the exact same support as the region we want to integrate over. However, it has some problems. As we can see, phi 1 of x and the product of fx times gx are not proportional in the region from 0 to 1. So the shape of fx times the absolute value of g of x is very different from that of phi of 1, which is flat. So let's see what exactly the function fx times absolute value of g of x looks like in the region between 0 and 1. So here's the R code that plots the curve of fx times gx, where x ranges between 0 and 1. And you can see that this looks like this. So it's e to the negative x divided by 1 plus x squared. And the uniform density is just a flat line over here. So you can see they are really different in their shape. In other words, we cannot minimize variance if we just choose the uniform density. For now, let's not consider the efficiency of this estimator using importance function phi 1, but let's just consider how we can implement this estimator inside R. So let's consider estimating theta with a total of 10,000 draws. So n is equal to 10,000. Then let's implement the 3 steps for the importance sampling. First step is drawing the x's from the importance function. So we know that in this case, our importance function is the density of the uniform distribution. So we just draw x following standard uniform distribution and obtain 10,000 draws. In step 2, we want to apply the transformation, which is g of x times f of x divided by phi of x, phi1 of x. And that, in this case, is given by the exponent of negative x divided by 1 plus x squared times the indicator function, testing whether x is between 0 and 1. So we just do times x is greater than 0 and x is less than 1 over here. In this third step, we want to take the sample mean of the gxfx divided by phase. That is given by theta hat 1, which is equal to the mean of gf of phi1. And we can see that theta hat 1 is approximately equal to 0.52. Okay, so now let's take a look at our second choice of phi. So phi of 2 of x is equal to e to the negative x, and x takes values greater than 0. This is essentially the exponential density with lambda equals 1. The advantage of this is that, first of all, like the uniform distribution, we know how to sample from phi2. We can either use inverse CDF or we can use the built-in function REXP inside R. Also, you can see that the phi2 function here, so e to the negative x, matches with the numerator of g of x times fx, which is equal to e to the negative x divided by 1 plus x squared. But it also has its limitations. The support for the exponential distribution, which is the entire positive line, set of positive real numbers, is much larger than the interval between 0 and 1. So what does this mean? This means that when we draw the samples from phi2, which is the exponential distribution, a lot of these samples will fall outside the interval between 0 and 1. And for these samples, the corresponding fx times gx divided by phi of x will evaluate to 0. And this will make our estimator very inefficient. So say we obtain a total of 10,000 draws, then many of them will be outside the interval between 0 and 1, and we won't be actually using them. So let's see the code that implements phi2. In this case, g of x times fx divided by phi of x will be equal to e to the negative x divided by 1 plus x squared, indicator x between 0 and 1, divided by e to the negative x. That's our phi2. And that is equal to 1 divided by 1 plus x squared of the times the indicator function that x is between 0 and 1. So let's try to implement this important sampling algorithm. First, we draw x from phi2. And that means we are drawing random exponential samples with lambda equals 1. So this can be done using the REXP function inside R. In step 2, we try to calculate this thing. So gx times fx divided by phi x for each of the draws we obtained in step 1. So gf phi2 in this case is this thing, which is given by 1 over 1 plus x squared times the indicator function that x is between 0 and 1. In step 3, we can just take the sample mean of what we obtained in step 2. And we can see that the theta hat 2 obtained using this method is also approximately equal to 0.52. So quite similar to what we got from the first method. So using phi1, that is the uniform density. Okay, so now is the time to look at our third candidate, phi3. Phi3 of x is given by 1 divided by pi times 1 plus x squared. And here, x can take any real number. You can see that this is the density of the standard Cauchy distribution. which is actually the same as the t-distribution with 1 degree of freedom. Thus, we can use the built-in R function, RT, to draw samples from phi3. And we can see that just like phi2, in this case, phi3 matches the denominator of the G that we tried to evaluate. It also has problems like the earlier exponential importance function. Again, the support, which is the entire real line, is way larger than the interval between 0 and 1. As a result, many of our RT draws will fall outside of 0 and 1, and the corresponding F times G divided by phi will be equal to 0, making the algorithm very inefficient. So let's implement this in R. In this case, gx times fx divided by phi x, where phi is given by phi3, is given by this fraction over here. You can see that some of the stuff in the numerator and the denominator cancel out. And then the result we get will be equal to pi times e to the negative x times the indicator function that x is between 0 and 1. To implement the importance sampling algorithm, it's quite similar to the first two cases. We first sample x from the phi distribution. So in this case, because phi is the t-distribution with the degree of freedom 1, we can use RT to draw 10,000 samples from it. In step 2, we calculate this ratio, pi times e to the negative x, times whether x is greater than 0 or less than 1. Because x is the t-distribution samples from the entire real line, you will probably expect that a lot of the x's will fall outside the interval between 0 and 1. So a lot of these will be equal to 0. In step 3, we calculate the mean of this thing. And we can see that in this case, our result is NaN, so not a number. What exactly is happening over here? So you can see that the gx times fx divided by phi x simplifies to pi, which is constant, times e to the negative x times the indicator. When we calculate e to the negative x, if we have really large, or actually very small negative x values, say negative 1,000, then e to the negative of negative 1,000 power, which is e to the power of 1,000, will be really large, and that will lead to overflow inside R. However, we know that the x's that are equal to 1,000, the value of 1,000 actually doesn't matter, because we know this part, the indicator part, will be equal to 0. So in order to avoid overflow, let's manually change the xi's whose absolute value exceeds 2 to 2. So this is done by adding an additional line after drawing the t random samples. We say that for any of the x's obtained this way that are greater than 0 in absolute value, so either greater than 0 or less than negative, that are greater than 2 in absolute value. So either x is greater than 2 or negative x is less than negative 2. So in these cases, we say we convert x to be equal to 2. That's fine. Changing the value is fine because we know for these guys, the evaluation of whether they're between 0 or 1 will fail anyways. So the rest of it is the same. We again calculate the ratio and take the sample mean. And this time we can see that the resulting theta hat 3 we obtained using phi 3 is approximately also equal to 0.52. So quite close to the other two places. And that should be true in general. So no matter what kind of importance function you choose, the resulting Monte Carlo estimator should be unbiased. So it should only fluctuate around the true value of theta. Okay, so we are looking at a lot of densities, but we're almost there. So let's look at our fourth candidate, which is V4. And that is given by e to the negative x divided by 1 minus e to the negative 1. Here, x ranges between 0 and 1. And you can see that this is actually a valid density between 0 and 1. So this distribution is actually the truncated exponential distribution with lambda equals 1 in the interval between 0 and 1. In other words, this density is essentially the conditional density of V2, the exponential 1 density, conditioning on x is between 0 and 1. So this is actually equal to V2 of x divided by large V2 of 1, which is the CDF of the exponential 1 distribution, evaluated at x equals 1. It has a lot of advantages. So first of all, the support is the same as f. So the support is between 0 and 1, which is the region we are interested in integrating over. Second, the phi4 given this way is proportional to the numerator of gx fx. However, there is no built-in function that we can use to sample from phi4, so we will need to write our own function. So we can do this using the inverse transform or the inverse CDF method we learned in the first week. In this case, the inverse of the CDF of phi4 is given by negative natural log of 1 minus u times 1 minus e to the negative 1 power. So I think I should have replaced this big U by small u, but you get the idea. So we can apply inverse CDF method to sample from the distribution with density phi4. First of all, we draw the samples from the standard uniform distribution, and then we apply the inverse CDF transformation. So we set our x to be equal to this inverse CDF function evaluated at our u draws. So our resulting x's will be the random samples from the distribution phi4. So when phi4 is equal to this thing, we can see that gx times fx divided by phi x is equal to this ratio over here. You can see some things on both ends cancel out, and the result will be 1 minus e to the negative 1 power divided by 1 plus x squared times the indicator function. We have already done step 1 in the code in the last page. So our x samples are already obtained. So let's directly go to step 2, where we try to apply this transformation. We say gf phi4 is given by 1 minus e to the negative 1 divided by 1 plus x squared, where x is our previous samples. And this is multiplied by the indicator function of whether x is between 0 and 1. And again, in step 3, we take the sample mean, and this gives us the theta hat using phi4 as our importance function. And again, this is approximately 0.52. All right, so we have one last density to look at. That's our phi of 5. Phi 5 of x is given by 4 divided by pi times 1 plus x squared, where x can take values between 0 and 1. So just like phi 4, the phi 5 defined this way is actually also a truncated distribution. You can see it looks quite similar to our phi 3. So this is actually the truncated Cauchy, standard Cauchy distribution, or the truncated T distribution with degrees of freedom 1, where the truncation is between 0 and 1. So phi5 of x is actually just the conditional density of phi3, conditioning on that our x is between 0 and 1. And this is equal to phi3 of x divided by phi3 of 1 minus phi3 of 0. So in this case, these are the CDFs for phi3. Just like our last truncated exponential distribution, it has a few advantages. It has the same support as f, and it matches the denominator of fx times gx, which we are trying to evaluate. However, again, this is a truncated distribution where we do not know how to directly draw from. So there are no built-in functions that does this. So we showed how we can use inverse transform to sample from the truncated exponential distribution earlier. What I want to show you here is a general trick or a general method you can apply to sample from truncated versions of well-known distributions between the interval a to b. So you truncate the distribution to where you condition on it's between a and b. In order to do this, we first get phi of a and phi of b, which are the two bounds, the p's corresponding to the two bounds under this distribution. So, for example, if we are sampling from the truncated Cauchy standard Cauchy distribution, then we want to calculate what is phi of a and phi of b for the standard Cauchy distribution evaluated at a and b. So this can be obtained using the pdist functions in R. So for example, pt, which will give you the p's, which is the CDF evaluated at particular values of the random variable, or like p norm or p binom, etc. So after you obtain phi of a and phi of b, which are two p's that are between 0 and 1, you want to sample your ui's, so your samples, from the uniform distribution between phi of a and phi of b. So your uniform samples will not be obtained from 0 to 1, but instead they're obtained between these two p's. After you obtain the uniform draws in the third step, you can transform them back to the x's you want. So let xi equals phi inverse evaluated at each of the ui's. So this can be obtained by using the qdist functions, for example, qt, qnorm, etc. in R. And by applying this, you will get the xi's, which are actually draws from the truncated distribution, where the original density is phi, small phi, and then it's bounded between some interval from a to b. So this might be a little bit abstract when I'm just talking about it. Let's see the actual example of sampling from phi5, which is the truncated t distribution with degrees of freedom 1. We want to do the truncation where a is equal to 0 and b is equal to 1. In this case, we first obtain uniform draws. So this is the combination of step 1 and step 2. We want to obtain 10,000 uniform draws where the bounds are given by pt, which is the CDF of the t distribution with degrees of freedom 1 evaluated at 0, and the upper bound is pt of 1. After obtaining these draws, we transform them back using the qt function, which is quantile function or the inverse CDF function. So we do qt of u, where u's are the uniform samples here, degrees of freedom 1. And then the resulting x's will follow the truncated t distribution with degrees of freedom 1. So here's a histogram of the x draws that we have obtained. So you can see that it does seem like all of the samples that we obtain are between 0 and 1, and the shape looks like a chunk of the t distribution between the interval from 0 to 1, which is nice. Okay. So now let's try to use our phi5, which is the truncated t, to obtain our estimate for theta. Here, the gx fx divided by phi x will be equal to the ratio here, which simplifies to pi times e to the negative x divided by 4 times the indicator function. We have already obtained draws from this truncated distribution in the last chunk of code. So let's directly go to step 2, where we try to apply this transformation. So gf of phi5 is given by pi times exp of negative x divided by 4 times the indicator function of whether x is between 0 and 1. And then in step 3, we take the sample mean of what is obtained from step 2. And again, the result is quite close to 0.52. So all 5 Monte Carlo estimators using different importance functions gave us approximately the same theta estimate. All of them are unbiased, so our question is, which one is more efficient? So if you're going to choose one or two of the importance functions we just tried, which ones are you going to choose that will result in the lowest MSE? In other words, the lowest variance of our theta hat. Well, an educated guess will be phi4 or phi5, because we know that we want our phi ideally to be proportional roughly to gx times fx. We have earlier looked at what that function actually looks like. And also we want the support of phi to be approximately the same as the support for our f. So an educated guess will be phi4 or phi5 will probably do the best out of all 5 options in terms of variance. Then because phi2 and phi3, which is the exponential distribution and the t distribution, have support that is way larger than 0, 1, a lot of the 10,000 samples will be outside of the region that we want to integrate. So they might be the least efficient. And let's see whether our code confirms this. So we can check this numerically by repeating each of the Monte Carlo estimations for 100 times. This will allow us to compare the variance or the standard deviation of the theta hat across the 100 replications. So specifically, what we want to do is for each of the possible phis and each of the theta hats we obtained using different phis, we want to repeat that for 100 times. So each time we obtain a total of 10,000 samples, we use one of the phis to get the corresponding theta hat, and we record that. We record 100 of such theta hats for each of the possible phis. And then we try to see across the 100 theta hats obtained using the same phi, what is the mean and what is the standard deviation of the estimates that we have obtained. And that will allow us to get a sense of what is the standard deviation or the efficiency of our estimators. Okay, so here's the code that does this. What we're going to do is to create first an empty matrix with 100 rows and 5 columns. So each row will correspond to one of the 100 replications, and each column corresponds to one of the 5 methods that we have implemented. So one of the 5 importance functions. So you know that for each of the columns, the results will be the theta hats that are obtained using one of the methods across the 100 replications. So let's first get it for phi1, which is the uniform importance function. The code is the same as before, except that this time we repeat this for 100 times. So for each of the 100 replications, we sample the uniform, do the transformation, and then calculate the sample mean. We store the sample mean, which is our theta hat, into the MCS matrix that we just constructed. So here's the code for doing that for phi1. Here's the same for phi2, phi3, phi4, and phi5. So you can see that here I broke it down to 5 for loops, so 1 for loop for each of the methods. The main purpose I did this is to trying to fit the code into the slides. So otherwise the code will be too long and then I cannot show them all on the slides. But when you do this, feel free to write all of them inside the same for loop. So we have replicated each of them for 100 times and have stored all of our results inside the MCS matrix. Let's take a look at the means and standard deviations obtained using each of the importance functions. Let's first look at the means. So the mean of the theta hats can be obtained by doing co-means. That will give us the mean of each column of this MCS matrix. And that is the average of 100 theta hats obtained using the same phi. You can see that all of them are quite close to 0.52. But what is more important is to compare the variance or the standard deviations. Because the smaller the standard deviation, the smaller the variance, the smaller the MSE, and the more efficient our theta hat is. We can try to get this using the apply function, where for each column of the MCS matrix, we apply the function that gets the standard deviation. And in order to display all the results, I have rounded everything to 6 digits over here. And here are the outputs. So each of the entries corresponds to the standard deviation of theta hat obtained using one of the phis. This is the result of using phi1, which is the uniform density. This is from phi2, which is the exponential density. Phi3 is the T density, and phi4 and phi5 are the two truncated densities. And as you can see, the standard deviations using phi4 and phi5 are indeed the smallest. And then the standard deviation of theta hat using phi2 and phi3 are very large, especially for phi3, where we have the T distribution over the entire real line. And then the uniform distribution we used is somewhere in between. So this hopefully gives you an idea that by implementing different kinds of importance functions, we can actually get Monte Carlo estimators of some integral of different level of efficiency, even if we use the same sample size of 10,000.